kinetic molecular theory. Now that sounds pretty crazy, pretty like big word, complicated kind of thing. But if we break it down, it's pretty simple. So kinetic, movement. Okay. Molecular, we should think molecules. Okay. Theory, we should think current idea. Could this theory change? Yeah, it could, but for right now, it is the current idea. Okay. So if we put this together, current idea. If we put this together, we should think the current idea about the movement of molecules. Right? So that's kinetic molecular theory. The two parts that we're going to talk about in this goal are right here. Parts A and part B. All atoms and molecules are in motion, always moving. In B, the motion of these atoms and molecules is random. There's no particular order to their movement. They are moving randomly. So those are the two parts we're going to talk about in this goal. The other parts down here, these parts, we're going to talk about in goal 3. Sorry, goal 4. Okay, so that will be next. So we'll come back to those. But for now, these two things: atoms and molecules are in motion, and the motion of these atoms and molecules is random. Okay, so we know that there are 3 states of matter. What you need to know about solids, liquids, and gases is here. Solids have a fixed shape and a fixed volume. So what that means is you have a solid, okay? You cannot change how much space that solid is taking up. If you crush it, it's still going to take up the same amount of space. Solids also have a fixed shape, meaning unless you're changing it physically, it's going to keep its same shape. Liquids, on the other hand, have a fixed volume, but not a fixed shape. So fixed volume, that means, a cup of water is going to be a cup of water is going to be a cup of water. But that cup of water could fill something like this shape, or it could fill something like this shape, or it could fill something like this shape. So there's no fixed shape to liquids. It can be poured into any of these and take that shape. But it does have a fixed volume. It's not going to take up any less or more space. And then we have gases. Gases do whatever they want. They do not have a fixed shape or a fixed volume. So they could fill any of these shapes. They could fill smaller shapes. Think about a balloon. You can put air into a balloon. You can squeeze that balloon and make the balloon smaller. So it can take up less space. And it can take up any space you want. It can be a big, huge balloon. It can be a small balloon. They can take up any shape that you put them in. All matter has 3 states. That's important to remember. All matter has 3 states. Does that mean that this table could be a solid, liquid, or gas? Yeah, it does. But it has to be at a certain temperature and a certain pressure. Okay? So at a certain temperature or a certain pressure, all matter could be a solid, a liquid, or a gas. Okay? So it's not just for water, it's for anything. Any metal, any solid, any liquid, any gas could be any of those states of matter. Solids. Okay? Solids, the particles are arranged very tightly together. Okay? You can see like there's no space in these particles. They're very close together, unless we're talking about water. which we'll talk about next. But for most everything else, particles are very close together. The movement, even though they're close together, they're always vibrating. They're always moving in place, just extremely quickly. Particles are always moving. It doesn't matter if it's a solid, liquid, or gas. So solids, particles are tightly packed together, and their movement, particles are vibrating in place. Liquids. And we have a little more space in between our liquid particles here. Okay? So particles are loosely packed together. The movement, particles are moving very freely. That's why they can take up any shape. They can take the shape of this straw. They can take the shape of this glass or this glass. So particles are moving freely, and they can take the shape of anything you put them in. Okay, so the arrangement, particles are loosely packed together, and the movement, particles are moving freely in a liquid. A gas. Now we have the particles even further spread apart. Okay, and the arrangement, particles are spread apart. They're spread apart more than they are in a liquid state or more than they are in a solid state. The movement, particles are moving extremely freely. They move wherever they want, whenever they want, and they're very far apart. So if we're thinking about density, okay, these particles, gas would be least dense, liquid would be next most dense, and the solids would be most dense. Okay, because remember, density is how tightly packed together those molecules are. So solids, most dense, liquids, next most dense, gas, least dense. Okay. Now let's talk about water. Water does not become more dense when it is in a solid state. This is the only substance that does this that we know of. For example, okay, let's say these are water. Let's say these are molecules. So in normal substances, this would be a solid. Okay, and then in the next goal, we're going to talk about how when you add temperature, particles move a little faster. They spread out. Okay, so this would be a liquid. And then this would be a gas. Okay, but for water, okay, for water, this might be a liquid. Okay, so here's our liquid water. Then when it freezes, the particles actually spread further apart. So this is why when you freeze soda in the can in your freezer, particles take up more space, and so your soda can explodes. The reason why they spread out is the hydrogen bonds spread the particles out in the solid state. Because there are hydrogen bonds connecting these particles, they spread out. Okay, so the solid state of water is less dense than its liquid state, which is pretty crazy. But just like all other gases, the gas is the least dense. Okay, I mean, there's a lot of things that happen because water's particles are spread out when they're in their solid state. Okay, if it wasn't like this, then lakes would freeze from the bottom up instead of the top down. We wouldn't have fish that would survive very long. So pretty crazy design how water works. Okay. All right, we're going to check out a quick video to see what happens when water freezes in a contained space. Okay, here we go.
These extreme temperatures, you would stay inside, but this is just like a huge laboratory for somebody doing science experiments. One of our viewers called and said that she heard a huge explosion in her garage during the night, and when she went outside, she found that it almost looked like there was snow all over. Maybe the roof had caved in. Come to find out, it was actually the culprit was a soda bottle. If you take a look at this one here, it's not completely solid, so there's still a liquid on the inside. It was sitting there, and the bottom puffed out just a little bit, just enough to fall over. The most vulnerable part of it is right here like this. It's under extreme pressure, so when it hits, there's a reaction. So here, watch this as it hits. Watch. After the explosion, the side bursts out, and you get this instant slushy that's inside. This is what she found all over her garage, and that sound of that gunshot explosion was the pressure released here when it happens, all because the liquid freezes, and when it freezes, it expands and falls over and hits the top.
Okay, so there was definitely some noise amplification there. You're not going to get that kind of same reaction, but yeah, that's what's happening. You have water that freezes, and when it freezes, the particles spread out and they take up more space. So they can't be contained in that bottle anymore, and it breaks. That's why you don't want water to freeze in your pipes, because it'll expand past those pipes and pipes will crack. You'll have water leaks in your pipes. So that's it. That's why water is unusual. Its solid is less dense than its liquid. That's pretty crazy. That's not normal. Okay, so that's it for this goal. We have reached the end. The end. Thanks for watching.